Welcome to Cookie's Maths and Science Hub. Today, we'll be looking at Pythagoras and trigonometry. Before we begin to discuss trigonometry and Pythagoras, let's have a quick refresher on what is a triangle. There are many different kinds of triangles. Let's look at the side-based ones first. There's an equilateral triangle, where all sides are equal. There's an isosceles triangle, where two sides are equal. There's the scalene triangle, where no sides are equal. However, we're going to be looking specifically at the right angle triangle, which has one angle equal to 90 degrees. This will be for both Pythagoras and trigonometry. Whilst there are rules that apply to the others, we're just going to focus on the right angled one in this video. The Pythagoras theorem as a whole states that the area of the squares of the three sides of a right angled triangle can be related in the formula a squared equals b squared plus c squared, known as the Pythagorean equation. We're not going to worry too much about that complex theory and just look at the equation itself. So looking at our triangle, we have what's known as the hypotenuse. This is the longest side of the triangle, and in the Pythagoras theorem, or the equation that is, it is given the denotation a. So this side, when squared, so a squared, is equal to the sum of b, the lower side, squared, plus c, the left-hand side, squared. Obviously, that's only in the example image I've provided. You can rotate the triangle and b and c are interchangeable. It doesn't specifically matter which side is which. Rearranging that equation using our algebra rearranging techniques, we can also solve for the other sides of the triangle using this equation. So we would get b squared equals a squared subtract c squared. Again, b and c can be interchanged. So you could also have c squared equals a squared subtract b squared. Okay, using this general concept, let's look at an example now. In this question, we're asked that given the triangle below, we need to find the hypotenuse. So remembering, the hypotenuse is the longest side of a triangle. So we're told that left-hand side is 5 meters, the bottom is 6 meters, and obviously we don't know what our hypotenuse is. So we have a squared is equal to b squared plus c squared. That's our equation. A squared is then going to be equal to 5 squared plus 6 squared. Now, when we use algebra, we talk about doing the opposite to both sides. The opposite of squaring a unit is to take its square root. So we take the square root of a, which gives us just a in our next line. And that means whatever we do to the left, we must do to the right as well. So that means we have a is equal to the square root of 25, 25 being 5 squared, plus 36, 36 being 6 squared. Taking the square root of that sum, we get a is equal to 7.81 meters. Now in this example, we've had meters. It's important to recognize that Pythagoras equations and such examples often deal with real lengths, meaning it's important to include units. This is especially important in physics concepts, where you're using this theorem to maybe work out displacement or velocity. We can then move into the concept of trigonometry. Trigonometry deals with the angles of a right angled triangle, and specifically the ratios of those angles and its sides. In a right-handed triangle, if we place our angle in the bottom right corner on this diagram, our hypotenuse is referred to as the hypotenuse and is the longest side of the triangle, as always. The side opposite our angle is, well, considered the opposite side. And the side adjacent to our angle is, you guessed it, considered the adjacent side. These are often represented by their first letter. So hypotenuse is H, opposite is O, and adjacent is A. There are three distinct ratios that relate our angle to the sides of our right angled triangle. There is sine, abbreviated to SIN, but still called sine. Cosine, cos, as it is also known. And tangent, often referred to as tan. Our sine of our angle, so that is the sine ratio of our angle, is equal to the opposite side from that angle over the hypotenuse. Our cos ratio of our angle is equal to the adjacent side over our hypotenuse. Our tangent ratio of our triangle is equal to opposite over adjacent. Now, it's important that you remember these three, and whilst there are many different techniques out there to remember them, I've often found the easiest to be the abbreviation SOHCAHTOA. That's SOHCAHTOA. So you can see that it's sine is opposite over hypotenuse, then cos is adjacent over hypotenuse, and tan is opposite over adjacent. We can use these ratios to solve for both unknown sides of a triangle as well as unknown angles within a triangle. Now, I didn't mention it at the start of the video, but it is helpful to remember that the three angles within a triangle, that is its interior angles, will always add up to 180 degrees. This can be helpful in some problems. Now, let's use this concept of trigonometry to solve for unknown sides within a triangle. The diagrams to the left will be used throughout this explanation. You can see that the opposite and adjacent change depending where the angle is within our triangle, as they represent the side opposite to the angle and the side adjacent to the angle. So if we move the angle, it's going to flip the sides. So all this is algebraic rearrangements with our ratios. So let's look at sine first. So we know that sine of our angle, and angles are often represented by the symbol theta, as it is in this diagram and in the text that will show up shortly. So sine theta, or sine of our angle, is equal to opposite over hypotenuse, or O over H. Therefore, if we were to perform algebraic rearrangement to get the O by itself, or the opposite by itself, we would have opposite is equal to our hypotenuse multiplied by our sine theta. This would then be the same for our hypotenuse, an extra step in the rearrangement, but we would get hypotenuse is equal to opposite over sine theta. This process can be repeated for cos of our angle, getting us the adjacent equal to hypotenuse multiplied by our cos of our angle, and our hypotenuse is equal to the adjacent over cos of our angle. It can then also be repeated for tan of our angle, where the opposite is equal to the adjacent multiplied by tan of our angle, and the adjacent is equal to opposite over tan of our angle. Let's use this idea now to go through some examples. In our first example, we're given the triangle below with a hypotenuse of 5 and an angle of 60 degrees in the bottom right corner. It's asking us to find the unknown side A. The first step in any of these questions is to figure out what sides you have present. So, as I stated, we know our hypotenuse, which means we're either going to be using sine or cos, as tan does not have the hypotenuse present in its equation. In that case, we then look for either the opposite or the adjacent side. In this problem, we can see that A, what we are trying to find, is opposite to the angle. Therefore, it is the opposite side. Given that we have the opposite and the hypotenuse, we will be using sine for this example. So sine of our angle is equal to opposite over hypotenuse. Therefore, our A will be equal to 5 times sine 60, because we substitute in our angle for the theta and 5 for our hypotenuse. Putting this in your calculator, and you should notice a sine function on your calculator, you will get A is equal to 4.33. Now there are no units on this one, so we don't need to include any units in our answer. Our next example asks us to find B, the unknown side in the triangle below. Once again, start by looking at your triangle. We have 40 degrees for our angle, and once again, we're trying to find B, which is our hypotenuse. So we know that it's going to be cos or sine. And looking at our angle, we can see we have the adjacent side, in this case, being 6. So that means we have our adjacent and our hypotenuse, meaning we use cos to find the unknown side in this example. So reminding you once more, cos of our angle, so cos theta, is equal to adjacent over hypotenuse. Rearranging for our hypotenuse in this case, or our b value, will mean that b is equal to 6 divided by, or 6 over, cos 40 degrees, because we substitute our angle in for that theta once more, which gives us b equal 12. Once again, not requiring units in this case. Our final example is asking us to find the unknown side c. Now these ones stand out straight away because we can see we have 5 and c as two sides, but hopefully you can see quickly that you don't have your hypotenuse. This is a dead giveaway straight away that we'll be using tan for this equation. So looking at our angle of 36 degrees, we can see its opposite side is 5 and its adjacent is c. So our tan of our angle, or tan theta, is equal to opposite over adjacent. So finding for our c, which in this case is our adjacent, we'll have c is equal to 5 divided by, or 5 over, tan 36 degrees, which gives us c is equal to 6.88. Now, I know those three examples didn't include units, but please remember to include them where relevant. We will now look at finding the unknown angle within a triangle using these trigonometric ratios. Much like for finding an unknown side, finding an unknown angle is simply using an algebraic rearrangement. To find an unknown angle, we look at each ratio individually. So if we are given the opposite and hypotenuse sides, we would of course use sine. Now, the opposite of the sine function is arcsine. However, you'll find it on your calculators as sine to the -1. They are slightly different functions, but that doesn't really matter now for this level of mathematics. So that means your angle by itself, or theta, would be equal to sine to the -1 of opposite over hypotenuse. This is then repeated for cos, where the angle, or theta, is equal to cos to the -1 of adjacent over hypotenuse. And tan has theta, or the angle, once more, equal to tan to the -1 of the opposite over adjacent. So let's look at some examples again. Given the triangle below, find the unknown angle theta. So if we look at our triangle, once more, you start by looking for the sides you have present. Seeing we have our hypotenuse, we know it's going to be sine or cos. So then we look for either the opposite or the adjacent. In this example, we are given the opposite. Now, a neat little trick here, because you are given two sides in these problems, you can use Pythagoras from earlier in the video to solve for the unknown side and then do a different ratio if you want to. I mean, it'll slow you down in the problem, but sometimes the problem will ask to find the side as well, which you can do either once you've found the angle using trigonometry or using Pythagoras. Regardless, for this example, we will use sine because we have our opposite and our hypotenuse. So sine of our angle is equal to opposite over hypotenuse from our initial formula. Therefore, theta, or our angle, will be equal to sine to the -1 of 4 over 5. So plugging that number into your calculator. Now, most calculators will require a shift or second key to be pressed so that you can click sine to the -1. Gives us theta is equal to 53.13 degrees. Our second example, we're trying to find theta once more. We can see we have our hypotenuse of 8, which means we'll either be using cos or sine. And we can see we have a side adjacent to our angle with a value of 6. So we will be using cos in this case, as we have adjacent and hypotenuse. So therefore, our theta will equal cos to the -1 of 6 over 8, which gives us our answer of theta is equal to 41.41 degrees. Our final example, we can see straight away we don't have our hypotenuse, so we'll be using tan in this case. Our opposite is 5, and our adjacent is 4. Therefore, our angle will be equal to tan to the negative 1 of 5 over 4. This gives us an angle of 51.34 degrees. Thanks for watching. Hopefully you've come away from this video with some key skills around applying Pythagoras to triangles and how to use trigonometry to find unknown sides and angles. Hope to see you back again soon.